Good morning. Today we will discuss on the vertical descent. If you remember, at the hovering flight in actuator disk theory, we learned that the wake is contracting and down in the wake, the velocity is twice the induced velocity at the rotor. Now, what about descent? Assume next that a helicopter is in a moderate descent flight. The descent speed is c and is directed, of course, upwards. If we consider positive direction down, it means that upstream the velocity of the air is minus c. At the level of the rotor, we have the velocity of descent c and the induced velocity vi. Because the rate of descent is between 1/4 of the induced velocity in hover and twice the induced velocity at the level of the for hover, it follows that at the level of the rotor, the total velocity, it is directed upwards. Downstream, so up in the rotor, we have again the rate of descent c and twice induced velocity as we learned from the actuator disk theory. It follows that the total velocity it will be c minus 2 vi and will be directed downwards. It follows that the air is passing through the rotor upwards, is deflected downwards, the disk periphery, and passes back through it. In this way, we see that we have a kind of turbulent region and airflow reversed up in the rotor. If we understand this, it follows that we can start to study different other descending flights. For example, in a slow descent, usually defined when the rate of descent of the helicopter C is smaller than 1/4 of the induced velocity in hover, we have again minus c down in the rotor. At the level of the rotor, the total velocity c minus vi directed downwards, and up in the rotor, the velocity, total velocity minus c plus twice induced velocity, this time again directed downwards. It follows that down under the rotor we will have the airflow reversed. The moderate descent on the right hand side picture we already have explained, so in this way we can go further. It means that there will be a region where the airflow will stay at the level of the rotor, which is the so-called vortex ring state condition. The unsteadiness of the airflow starts when the rate of descent is 1/4 of the induced velocity in hover, peaks at 3/4 vi in hover, and disappears at 1 and 1/4 of the induced velocity in hover. If we increase further the descending speed c higher than twice induced velocity in hover, it means that we will have the same direction of the flow, and actually the rotor will extract energy from the wind. It is the so-called windmilling state. If you understood this, we can put them all together. So the helicopter is going from hover in a climb. In the same way, the wake is contracting down in the wake. The slow descent, where the downwash will still dominates the flow. In a vortex ring state, where an upwash is approximately equal with a downwash, and the windmill break, where the net flow through the rotor will be upwards and the rotor will extract energy from the flow. I added to this class a movie of Jan Drees who visualized for the first time these helicopter states. He also visualized the vortex ring state. he showed that actually it is a kind of bubble which is forming at the level of the rotor, that the bubble grows in time, the bubble will explode, and then again the bubble will reform. The vortex ring state, it will be entered when the helicopter will descend from 300 feet per minute to 600 feet per minute, and we pass the vortex ring state at 1500 feet per minute and 3000 feet per minute. In the vortex ring state, as I said, it is like a donut of air swirling up and around the blade tips, which is a vortex ring. The rotor will pump air into this big bubble, it will fill it up, and then periodically it will explode every second or two. It follows that in a vortex ring state we will have a change in thrust and power, and the rotor flapping will be erratically, and the helicopter will pitch and roll. This is a state where the helicopter pilot has to get out as soon as possible. Why? The problem that are here are the so-called settling with power in vortex ring state. So in this state, the helicopter experiences a rate of descent of at least 300 to 500 feet per minute at an airspeed of no more than 10-15 knots, with more than 20% power applied. So if we do not have thrust, we need to apply more power. However, in the vortex ring state, we can find ourselves in a problem of out of power. The power settling is defined as a broad category of phenomena where stalling of the rotor blades are happening and the rotor system is losing lift. What are the problems in the vortex ring state that we have as engineers? You see here a graph of the function of the velocity through the rotor and the descent velocity, the rate of descent. They are non-dimensionalized with the induced velocity in hover. You see that actually the theory predicts a kind of descending line. As we are moving, as we are increasing the descent speed, the net velocity through the rotor is decreasing. However, the tests that have been done, for example, at Georgia Tech show that in this region, first there is a small decrease, but afterwards there is a high increase. So moving from hover into descent, the induced velocity increases more than rapidly as actuator disk theory would indicate. The values rises in the vortex ring state to about twice the hover value and then falls steeply to about the hover value as we enter the windmill brake state. Then it means that we have little tools to predict the vortex ring state of the helicopter. The problems in the vortex ring state. The theory shows that if the angle of attack is decreasing, the lift is decreasing and there is a loss of thrust. However, the angle of attack is decreasing, it means also that the lift is tilted backwards and that the induced drag increases and more power is required. The pilot problem, it is the settling with power. Pulling up the collective stick will not slow the rate of descent. The helicopter will come down even though full engine power has been used. Some problems in the vortex ring state, as I mentioned, is that we have a lot of fluctuation in the engine power and, of course, in the collective pitch position. Here you see again a representation of the engine power and the collective pitch as a function of the rate of descent. You see the region of power settling where actually we need more engine power that predicted by the theory. If we do not have enough engine power, it means that the helicopter will fall quicker from up. The rate of descent, if it is higher than 1.25 the induced velocity in hover, the worst of the thrust and flapping fluctuations will disappear. Here you see the Bell Jet Ranger and again the rate of descent and the rotor thrust. For example, if you look at the curves, you see that if the velocity of descent is smaller than 500 feet per minute and higher than 1500 feet per minute, the curves are stable. In between, the system is unstable and a small increase in the velocity of descent will result in thrust smaller than weight. Therefore, in order to keep thrust equals weight, we have to increase the collective pitch. If we do not have enough collective pitch applied to the helicopter will falling faster and faster. This was also the cause of the Osprey accident in Arizona. In 1992, a V-22 crashed in Arizona at 2,000 feet per minute descent rate at 40 knots with an angle of descent of 26 degrees. Here you see again the descent angle and the thrust of the Osprey. The problem is that actually the condition when we are descending at a smaller angle of descent, it is more dangerous than decreasing with a 90 degrees descent angle. Consider in this graph a line of constant thrust. To keep the thrust equals weight, we must first reduce the collective. Assume that the pilot is starting to descend from the level flight at point A. At first, he has to reduce the collective. At point B, when we achieved, let's say, 30 degrees of descent angle, the trend reversed, and to keep the thrust constant, we must increase the collective. The V-22 has two rotors, and the vortex ring state thrust fluctuations do not act the same way to thrust fluctuations. For example, if a small roll to the right happens, the right rotor will drop, the descent angle will increase, and we will lose even more thrust. The left rotor will rise, and we will gain thrust. Therefore, a divergent unstable rolling will start to appear, which is very difficult to stop. So the pilot will need more and more thrust in one rotor. After this accident, there has been an operational constraint on the V-22 operations. It is that the V-22 was allowed to operate at a descent rate of 800 feet per minute at 40 knots. Vortex ring state is affected by twist. Here you see an example of rate of descent and the induced velocity and the power required for an untwisted blade and a minus 12 degrees twisted blade. You see that the fluctuation of the forces and moments on the rotor with twisted blades are larger at higher rates of descent and then in a rotor with untwisted blades. The case that we are showing is for a Bell H1 Cobra. And for example, in this helicopter, there was no twist in the tail rotor blades. And they had excellent flying qualities when it was flying through the vortex ring state. Why? Because untwisted blades are more heavily loaded and then a stronger tip vortex is stabilizing the flow. The tail rotor can also find itself in the vortex ring state. See here a problem. what is happening when the tail rotor it is in the vortex ring state. For the Apache H64, the prototype in the left-hand side of Apache, it had a T-tail, and the result was that if you in a pedal position in the pilot control, if you plot as a function of the sideward speed, there was a thrust instability which can be associated with high activity in the pedals in order to maintain headings. So sometimes the pilot could not hold the sideward flight. The designers then changed the Apache and installed an stabilizer, as you see on the right hand side of the figure. They also approached the tail rotor to the main rotor. You see immediately that the pedal position, it is much better now when the helicopter is passing, when the tail rotor is passing through the vortex ring state. In this way, the situation was improved. If the tail rotor is in the vortex ring state, this appears if we are flying, for example, in a right sideward flight, where the main vortices of the rotor are sucked into the tail rotor. As I said, the Bell H1 Cobra had no twist in the tail rotor blades and it had excellent flying quality. Also, executing a right hover turn can be also transformed from a slow turn into a fast turn if the tail rotor is loses thrust in the vortex ring state. Finally, I give you another tail rotor problem and the solution herein. Namely, the direction the tail rotor is turning. You see here a picture of the Lockheed Cheyenne and the pedal position as a function of the left sideward flight. On the left hand side you see the original direction of rotation. In the left sideward flight the pilot ran out of the pedal. You see the red region, and that happened between 14 to 18 knots as he was trying to get out of the vortex ring state of the tail rotor. Therefore, the direction of the tail rotor was changed, and you see that now the pilot was out of the problem. Also, noise in forward flight is lower if the blade at the top of the tail rotor is going aft, which solves more or less both problems, the vortex ring state and the noise problem. I end today this lecture qualitatively describing the vertical descent of the helicopter.